Dear colleagues, dear professors, dear guests, good day. Uh, I'm Mohammed Taha. I'm working at Yozgat Bozok University Veterinary Medicine Faculty. So today I will present you ferroptosis and kidney injury therapeutic perspectives in diabetic nephropathy. What is the diabetes? Actually, diabetes is defined as a metabolic disease characterized by chronic hyperglycemia resulting from impaired insulin secretion, impaired insulin action, or both. We have two major diabetes, type 1 and type 2 diabetes. Type 1 diabetes is the pancreas cannot produce insulin because the immune cells attack the beta cell and can lose the beta cell, and pancreas cannot produce insulin. In type 2 diabetes, pancreas can make less insulin for the use, or the body produce enough insulin but cannot use because of the insulin resistance. So, in diabetes, also prolonged hyperglycemia affects various organs and tissues, leading to macrovascular and microvascular complication. Diabetic nephropathy is complication that leads to end-stage renal disease can ultimately result in death. Chronic hyperglycemia is considered one of the main causes of diabetic nephropathy. Approximately 30 or 40% of diabetic patients develop diabetic nephropathy. What is the pathogenesis of diabetic nephropathy? Actually, chronic hyperglycemia can cause the kidney damage via many pathways, and can activate many Stokins F factors. Also, chronic hyperglycemia can cause reactive oxygen species. This reactive oxygen species can contribute to kidney damage. Also, reactive oxygen species can elevated advanced glycylation end products, also elevated protein kinase C. Also, they can activate it to nuclear factor kappa beta MAP-key pathways. Also can produce inflammation in kidney. Also, these reasons can cause the kidney damage. Also, reactive oxygen species can trigger to many Stakins, transform growth factor beta and VGF, vascular growth and vascular endothelial growth factor. But this can cause elevation of mesenchymal cell proliferation and glomerular basal membrane thickness. Also, this can cause in progression of diabetic nephropathy. Also, hyperglycemia, also reactive oxygen species, can cause apoptosis in tubular kidneys and podocyte cells. Also, this can cause progression of diabetic nephropathy. Also, renin-angiotensin-aldosterone system activation can cause apoptosis in renal cells, and this reason also can cause the progression of diabetic nephropathy. Also, ferroptosis is a regulated form, a cell that distinct from apoptosis and necrosis, characterized by iron defense and lipid peroxidation. Also, ferroptosis can main role in diabetic nephropathy, also many diseases. So, for this reason, ferroptosis inhibiting treatments are expected to be applied in coming year. In recent years, the use of phytotherapeutic substances has been increased and plays an important role preventing the progression of diabetic nephropathy. Also, we are not fully elucidated ferroptosis role in diabetic nephropathy. Also, we don't know the significance of the ferroptosis in diabetic nephropathy. In this review, aims to provide insight to the potential mechanism of ferroptosis, its role in the diabetic nephropathy, and effects of various phytotherapeutic interventions on diabetic nephropathy. So, what is the diabetic what is the mechanism of ferroptosis? First of all, accumulation of iron can cause produce the reactive oxygen species. Also, too many accumulation of iron can cause or produce reactive oxygen species. This reactive oxygen species produced via Fenton reaction. This arrows reactive oxygen species can cause the lipid peroxidation. They peroxidate to polyunsaturated fatty acids. This also acetylated by AGSL4. This enzyme is the carrier of the ferroptosis. Also, these acetylized PUFAs can produce many toxic lipid peroxides. If they excess accumulation of this toxic lipid peroxides can cause ferroptosis in cell. Also, cysteine or glutathione coenzyme of the GPX4, it's a main role of the detoxifying enzyme in ferroptosis. Cysteine or GCH glutathione depletion can cause the inhibition of glutathione GPX4 enzyme, and this causes also ferroptosis in kidney. So I will like to tell you some phytotherapeutic substances on diabetic nephropathy, and we will see what is the effect of these substances in diabetic nephropathy. So glabridine, this is the planted isoflavone derived from the roots and rhizosome and Glyceria glabra, and they have many effects in diabetic models and many studies. So also Tan et al. Reported the glabridine increased the activities SOT, GSH, and catalyst, and in diabetic plus unregulated GPX4s, SCLC7A11 and CLC3A2 expression, and downregulated TFR1 vascular endothelial growth factor, and PAKT and PRIK1/2 expression, thereby reducing MDA levels and iron accumulation both in vitro and in vivo. Collectively, these findings indicate glabridine suppress ferroptosis by mitigating oxidative stress and delay progression of the diabetic nephropathy by inhibiting VEGF-AKT signaling pathway. Calcitonin. Calcitonin is isoflavone phytoestrogenic derivative Astragalus membranous. Also exhibits a broad range of pharmacological activities. Huang et al. Reported calcitonin improved kidney function in diabetic mice, elevated tubular injury, and enhanced the viability of EQ2 cells exposed to high glucose. They further demonstrated calcitonin in protective effects in diabetic nephropathy by suppressing ferroptosis, as evidenced by reduced levels of lactate dehydrogenase mediated and lipid rose, alongside significant increased GPX4 expression driven by elevated GCS activity. Magniferin, a natural flavonoid that is derived from mango, it has been wide range of pharmacological activities. Also, it has been demonstrated magniferin enhances melatonin-mediated anxiety system, can cause SP1Q10 axis and GPX4 in diabetic rats, thereby reducing AGSL-mediated lipid peroxidation and preventing ferroptotic cell death in kidney. Glyceric acid is the terpene isolated from medicinal plant Glyceria glabra and exhibits diverse pharmacological activities in many studies. Recent studies have shown that glyceric acid upregulates GPX4 expression and reduces reduced oxygen species production in the mouse glomerular podocytes exposed to high glucose. These findings indicate that glyceric acid elevates high glucose-induced podocyte injury likely through the inhibition of ferroptosis. Ginkgolate B is a diterpenoate is from the ginkgo biloba leaves exhibit multiple pharmacological properties. Recently, Chen et al. Reporting concluded B upregulates ferroptosis-related proteins, ferritin heavy chain, and GPX4 while downregulating TFR1, thereby reducing reactive oxygen levels and intracellular iron accumulation. They further demonstrated that ginkgolate inhibits ferroptosis by preventing biobutykin-mediated degradation GPX and sustaining GPX protein. Anthraquins, also sennosid A, it's a bioactive compound. They can derive from rhubarb and senna plants. So in diabetic mice, sennosid A has been shown to suppress ferroptotic cells by reducing PTGS2 protein expression, MDA levels, and changing HCS activity and GPX expression and modulating NF2 and HO1 signaling pathway. Also, the last one is the umbelliferone. The umbelliferone is the coumarin compound derived Ecomnia cortex, Pronella spica, and Angelica dahorica. It's been reported to exhibit diverse biological activities in many studies. So, umbelliferone increased GCH activity by inhibiting ROS production in diabetic mice and high glucose-induced TK2 cells while reducing MDA levels and iron accumulation, upregulation GPX4, and NRF2 and HO1 expression, and downregulation AGSL4. These findings indicate that umbelliferone exerts inhibitory effects on oxidative stress and ferroptosis both in vivo and in vitro. Conclusion. Increasing evidence indicates that ferroptosis plays a critical role in the pathogenesis and progression of the diabetic nephropathy. Hyperglycemia-induced oxidative stress in iron overload, excessive lipid peroxidation contributed to GPX4 inactivation, glutathione depletion, ultimately triggering ferroptotic cell death. This process promotes podocyte injury, tubular dysfunction, and glomerular damage, all of which are the hallmarks of diabetic nephropathy. Although no clinically approved therapies currently target ferroptosis directly, recent studies highlight the therapeutic potential of various natural compounds, phytochemicals such as glabidin, calcicin, magneferin, glyceric acid, ginkgolate B, sennosid A, and umbelliferone have been shown to modulate ferroptosis-related pathways by changing GPX4 activity, restoring GCH levels, and reducing ROS and lipid peroxidation, regulating iron homeostasis, and influencing K signaling pathways, including ACL4, TFR1, and NRF2-HO. These renoprotective effects suggest that targeting ferroptosis may offer a promising and new direction for the diabetic nephropathy management. Further experimental clinical studies are needed to validate the findings, determine optimal dosing strategies, and assess long-term safety and efficiency. Oral ferroptosis represent emerging therapy target and natural compounds with antiferroptotic properties may provide valuable adjunctive strategies for slowing, preventing the progression of diabetic nephropathy. Thank you for your attention.